Imagine printing an actual rocket engine entirely from scratch. Pretty wild, right? Well, welcome to this explainer. Today, we're taking something that's been a massive buzzword for the last decade, 3D printing, and we're going to completely demystify it. We're cutting through the hype to unpack the actual reality behind additive manufacturing. We'll look at how it works, what it's made of, and exactly why it's shifting from, a prototyping novelty into an absolute powerhouse of a tool in modern industry. Let's get into it. So, here's our game plan for this explainer. First, we'll cover the basics of additive manufacturing, then walk through the 8 steps to print. After that, we'll dive into the materials driving the future, explore the different types of tech, and finally, we'll wrap up with the really crucial art of part orientation. All right, Section 1, Basics of Additive Manufacturing. Let's move beyond the buzzword and get our fundamental definitions absolutely crystal clear. Now, to really understand additive manufacturing, or AM, we first have to understand what it's not. Think about traditional manufacturing. It's usually a lot like sculpting a statue out of stone, right? You carve away the waste. Or maybe you're forcing molten material into a mold under intense heat and pressure. Well, additive manufacturing flips that script entirely. It's honestly much more like building with Lego. You take virtual 3D computer-aided design, your CAD data, and translate it into physical models by adding material in a strict layer-by-layer sequence. You're building up instead of taking away. Think about the contrast here. With formative manufacturing, like injection molding, you're filling a shaped cavity. With subtractive CNC machining, you're literally carving a shape out of a solid block of metal or plastic. But additive? It starts with absolutely nothing. A nozzle or maybe an energy source selectively deposits or fuses material exactly where it needs to be, layer upon layer until, boom, the final shape is formed. It's a completely different paradigm for making things. So you might be wondering, if it's so great, why aren't we just 3D printing literally everything? Well, it all boils down to economics. With additive manufacturing, your cost per part basically stays flat regardless of volume. Whether you need 10 complex parts or 100, the cost per unit is pretty much the same. But with formative manufacturing, like injection molding, the initial cost is incredibly high because, you have to custom build the mold. But once you scale up to thousands of parts, that cost per unit absolutely plummets. So additive manufacturing is absolutely unmatched for low volumes, super complex custom designs, and rapid turnarounds. But for identical, massive-scale mass production, traditional formative methods still win out. Moving right along to Section 2, the 8 steps of AM. Let's trace the actual journey from a digital concept on a screen to a physical object you can hold in your hand. The first half of this journey is completely digital. It kicks off with your CAD design, where you define your exact objectives in software. That concept is then translated into an STL or OBJ format, which is essentially the language your printer speaks. Then comes the real magic, slicing. This is where the software takes your file, orients it on a virtual build plate, and literally chops your 3D model into thousands of flat 2D horizontal layers. It's exactly like slicing a loaf of bread. Finally, you move to machine setup, dialing in nozzle temperatures, leveling the build platform, the whole shebang. Now we get physical. The build itself is mostly automated, but here is where a lot of people actually get it wrong. The process does not end when the printer stops, not even close. Once the build is done, the real dirty work begins. You have to physically pry the part off and remove any temporary support structures. Then comes crucial post-processing. We're talking washing away uncured resins and alcohol, vapor smoothing, or sanding down rough edges. Only after all of that is it finally ready for its application, meaning actually integrating your newly printed part into its final real-world system. Okay, Section 3, Materials Driving the Future. If you still think 3D printing is just for making brittle plastic trinkets, prepare to have your mind changed. The sheer diversity of printable materials today is just staggering. We aren't just using standard structural polymers like nylon and ABS anymore. We are printing directly with aerospace-grade titanium and stainless steel powders. We've got advanced ceramics like alumina and composites that let us use ultralight carbon fiber. Literally, there are even specialized bioextrusion systems processing biocompatible hydrogels for actual human tissue engineering. I mean, the material science driving this industry is evolving practically every single day. Let's jump to Section 4, Types of 3D Printing Tech. Now that we know what we can print, let's look at the incredibly varied machines that actually do the printing. Additive manufacturing isn't just one magic box. It's an expansive, rapidly growing family tree. These branches classify different processes based on exactly how raw liquids, solids, or powders get fused together. You've got vat photopolymerization, material extrusion, powder bed fusion. Honestly, it is super easy to drown in all the acronyms here. So let's simplify things and just compare a few of the heaviest hitters in the ecosystem. Let's start with two really common polymer processes. First up, vat photopolymerization. I know, it's a mouthful, but this includes SLA, which uses a highly precise UV laser to cure a pool of liquid resin layer by layer. It's absolutely perfect for high detail stuff like jewelry molds or dental aligners, though the final parts can be a bit brittle. Contrast that with material extrusion, or FDM. Think of this like a highly precise robotic hot glue gun, squeezing out molten plastic filament. It's fast, it's low cost, and it uses really robust plastics, but it does yield a noticeably rougher surface finish. Now, what about metal? This is where it gets really wild. Powder bed fusion uses a high-energy laser to melt microscopic particles of metal powder together. The amazing thing here? You actually don't need to print support structures because the loose, unmelted powder surrounding the part acts as a cushion and holds it up during the build. This allows for fully dense, wildly complex geometries. On the other hand, we have direct energy deposition, or DED, which injects metal powder directly into a laser melt pool. Its superpower? Let's say you have a $100,000 jet turbine blade with a tiny crack. Instead of tossing it, DED can literally heal the metal by adding material directly back into that worn-out spot. It's a real game changer for repairs. Finally, Section 5, the art of part orientation. We've talked a ton about machines and materials, but here is where the human element really takes center stage. How you digitally place your 3D model on the virtual build plate, it changes literally everything. Orientation impacts stair-stepping, which is how smooth a curved surface ends up looking. It completely changes the volume of wasted support material, your total build time, and how many parts you can squeeze onto one plate. But critically, it affects mechanical strength due to something called anisotropy. Basically, think of a 3D printed part like a piece of wood. It's super strong along the grain, but much, much weaker across it. You have to intuitively orient the part so the real-world physical stress doesn't just snap it right at this horizontal layer lines. Picture the exact same part, but oriented 3 different ways: vertical, horizontal, and inclined at an angle. To hold these shapes in midair, the printer has to build temporary support structures underneath them. A vertical orientation might require a massive, wasteful scaffold just to hold up some arches. An inclined orientation can be an even bigger mess. But a horizontal orientation, it usually sits almost completely flat against the bed, requiring barely any extra support scaffolding at all. And when we look at the hard data, the difference is staggering. A horizontal orientation often requires nearly half the wasted support volume of a vertical setup. And speed? It finishes hours faster than the inclined version. We're talking wrapping up in about 8,400 seconds compared to over 13,000. Simply by rotating the part on a screen before hitting print, a smart operator saves massive amounts of time, raw material, and money, all while yielding a much stronger final product. So we've covered a lot of ground today. We've moved from the core definitions and the step-by-step processes, to the materials, the very technologies, and that hidden human art of part orientation. Additive manufacturing is clearly no longer just some futuristic sci-fi concept. It is a highly optimized, calculated science that is fundamentally reshaping supply chains, medicine, and aerospace right now. So I'm going to leave you with this final thought. As additive manufacturing continues to scale up, break boundaries, and edge closer and closer to mass production, what will you build layer by layer? Thank you so much for joining me on this explainer. Keep learning, and I'll catch you next time.